inviting me to give this lecture. Today I'm gonna talk about the state and the fate of Antarctic ice shelves, and looking at it from a modeling and remote sensing perspective. And most of the work I'll be presenting today is actually work being done by my team of PhD students. So I'd like to start by definitely acknowledging them here. Most of the hard work and the dirty hands is part of their work. And I'm probably preaching to the choir here to say that sea level rise projections are a key component in future climate, and depending on which emission scenarios we will follow, might reach very high levels or unprecedented levels over the last centuries. Where depending if you go for a high emission scenario, we might reach more than 3 meters by 2300. And if you look at these sea level rise projections, thermal expansion and glaciers are probably the most important ones, at least this century, followed by Greenland and Antarctica. So if you look at the absolute numbers, Antarctica doesn't make the podium, or at least not in the average scenarios. However, if you look at the uncertainties that come with these projections, so if you, for example, for the RCP 8.5 scenarios, look at the uncertainties, we actually see that Antarctica is the largest uncertainty if we talk about future sea level rise projections. And one of these uncertainties, or one of the key drivers for the uncertainties, is actually the role of ice shelves. Ice shelves are the gatekeepers of Antarctica. They do not directly contribute to sea level rise because they're already floating, but they buttress the ice, and by buttressing the ice, they actually slow down the ice flow from the ice sheet. So although they do not directly contribute to sea level rise, they indirectly do. You can see it a bit as an analogy. As a slow car in traffic, the car itself does not change the traffic, but it's actually slowing down all the traffic behind them. And if you look at all our ice shelves across Antarctica, we see that they actually the buttressing effect, so the slowing down effect, is actually very large. Some of them have some passive areas, like Ross Ice Shelf or the Filner ice shelves, but most ice shelves actually have a very strong buttressing effect. So they slow down sea level, they slow down mass loss, and therefore sea level rise. And if we look at how Antarctica is doing, although Antarctica was lying a long time being perceived perhaps as a sleeping giant, we see that the giant is no longer sleeping. Actually, that Antarctica is losing mass, specifically in some areas, like on the peninsula, the Amundsen Sea Embayment, or on the Totten area. There's other areas where it's slightly gaining mass, but on average, Antarctica is losing a lot of mass. And it's concentrated in some hotspots, and all these hotspots are actually related to the response of ice shelves. One of these hotspots is Larsen B, or the ice shelf as a result of the response of Larsen B. The collapse of Larsen B ice shelf is probably one of the most iconic, or at least to me, most iconic satellite image series taken by the MODIS satellite. So if you look at Larsen B in 2002, prior to its collapse, you actually can see all these blue dots here, which are individual surface lakes, and these lakes resulted in a hydrofracturing event, which gradually, or actually rather abrupt, over a time period of a couple of weeks, resulted in the complete or the partial collapse, and large part completely collapsed over a very short period of time, removing the entire ice shelf. And when this ice shelf was gone, the buttressing effect was gone, and the glaciers started to contribute quicker to sea level rise. Other hotspots of change are the other side of the peninsula, the Amundsen Sea Embayment of the Totten area. And again, there these mass loss, or this hotspot of mass loss, is related to the response of ice shelves. Here we see strong mass loss, and this mass loss can be related to the availability of warm ocean water, relatively warm ocean water that melts away the ice shelves, or the ice front at
bottom. So you see that these areas actually correspond to areas here in this figure of Adusumili in green. So areas where we actually have warm ocean water that melts away the glaciers. So you actually again see that everywhere where we saw these hotspots, these are also the areas where we actually have a availability of warm ocean water. And so understanding the response of ice shelves is key if we want to understand future mass loss from Antarctica. And to understand these processes, there's actually three processes that I consider key. And one of them is surface melt, like on Larsen B. Ice shelves can melt at the top due to warm temperatures, form lakes and result in hydrofracturing. Or they can melt from the bottom due to the availability of warm ocean water, thinning the ice shelves. And both of them would result in an increased ice flux, contributing to mass loss. A third component is damage. Actually, these ice shelves can also start to fracture. They can start to weaken. And then once that happens, again, we see that ice shelves can increase the ice flux and so contribute to mass loss. And today I'm going to talk about what our team is doing with remote sensing images and some modeling to understand each of these three processes. So surface melt, basal melt, and hydrofracturing. And let's start with surface melt and hydrofracturing. Here you see how lakes on an ice shelf might look like. This is for George VI. And so you can see that actually on this ice shelf, a lot of ponding of lakes happens. And we don't only see that here on George VI, or we don't only see that on the Larsen B example. There's also a rather recent example of hydrofracturing. And this is the Milne ice shelf in the Arctic, so the other part of the world, but actually a very similar process where we see that the Milne ice shelf during summer, there's a lot of ponding of individual lakes on this ice shelf. And so last summer, August, end of July 2017, there was a hydrofracturing event happening on this on this western side, resulting in a large collapse and then a large loss of the ice shelf. And if you look at these satellite observations and you try to understand what the water actually does, so for example, if we calculate for each of these lakes the lake depth, so based on the penetration depth of light, we can estimate lake depths for these lakes. You actually see that on the location where the event happened, so here on the left, indicated here with my on this area, we actually see that there is the location where we actually see the formation of the deepest lakes. And these lakes, due to their weight, resulted in a load, resulted in additional stresses that eventually resulted in a fracture. Here we see in high resolution planet images, for example. So you see the individual lakes being filled here, especially where they're very dark, they're very deep. And if you then subsequently just post the fracture, you actually see that this ice shelf completely scattered into very small pieces as a result of this load of hydrofracturing. So in that sense, hydrofracturing is a very abrupt event that can actually on a very short time scale remove large parts of ice shelves or completely. And it's an interplay of stress and water availability. So you need a weak ice shelf or you need enough water load to actually weaken this ice shelf. And a recent paper by Lai and colleagues, for example, quantified the potential of ice shelves across for hydrofracturing across Antarctica, identifying areas where actually if there would be water available, if there would be ponding, they would be very vulnerable, and where we see that most of these ice shelves actually show a very strong vulnerability, and other areas would be vulnerable only if the lake depth would exceed a certain depth. So there is a strong sensitivity for these ice shelves, and it can be a potential
important component. Now, the second thing we need, if we need hydrofracturing, is we need
Stef,
Yes,
can I interrupt you a second? There's a question in the chat.
Okay, sorry.
Do you mind if we spontaneously interrupt you?
No, I prefer that even.
Great. So there's a question from Vivian. Are the lakes that you see associated with hydrofracturing associated or aligned with crevasses?
So the lake is it's Milne ice shelf, so it's in the Canadian Arctic. So a bit north of Greenland actually, and so in terms of their alignment, so let me see if you look, so this is prior, so you see that the lakes they would be aligned like this, and you see that there are already pre-existing some of these crevasses. Of course, there's also rifting on this ice shelf. Also, if you look here on the event itself, you see that actually here it fractured or it scattered into small pieces, and actually this piece, which is the result of a rift, more kind of resulted in I think it's this one. You see this piece stays intact, but also is being kind of, it floats away. So here you have a large, more tabular iceberg. Here actually there is this scattering into smaller pieces. In terms of alignment, you actually see that all of these fractures align a bit with the lines of the lakes. I don't know if Vivian, if that responds to your question.
I think it's good.
Okay, very good.
Thank you very much.
You're welcome. I'll have a look at the chat as well, so I'll try to multitask here. So the next thing what we need if we talk about hydrofracturing is that we need enough meltwater, of course. And if you look at the future projections, for example, from global climate models, we see that very much depending on which scenario, if we take a high or a low emission scenario, we might reach very divergent trajectories in terms of the amount of meltwater available. And here you see it for the different periods. And here you see it as surface melt on a map. So with strong hotspots all over the peninsula, George VI, and a part of the Bellingshausen Sea. So we expect a lot of surface melt. And if you then look at how much melt would we need, typically now we use thresholds like the amount of meltwater that we needed for the collapse of Larsen A and Larsen B as some sort of thresholds. So this red line here is often considered the threshold of how much meltwater do you need to have enough meltwater available to hydrofracture. And see that in current, by mid-centuries, most ice shelves do not surpass this threshold. But if we go further in time with the high emission scenarios, we definitely see that, for example, for Larsen, for Wilkins, for George VI, there might be enough meltwater to surpass this threshold. But of course, these thresholds are I think, back of an envelope approximations. If we actually want to estimate the potential for hydrofracture or the effect of hydrofracturing, we need to quantify these things better. And that also means that we have to better estimates of melt. And this also needs, this results in a better need of process understanding. In some recent work we did a couple of years ago on the Robodois ice shelf, we identified, for example, that when you look at melt climates over these ice shelves, they're very much located on the grounding line as a result of wind-albedo interactions. Actually, there's a local microclimate which makes the grounding lines of these ice shelves extra warm. How does it work? We typically have katabatic winds flowing down. Whenever they reach the grounding line, due to the change in slope, they typically result in vertical mixing of the air, pulling down warm air from the atmosphere to the colder surface. So you have some vertical mixing resulting in a warm local microclimate in this area. At the same time, the winds are very strong there, so we have a lot of snow erosion, and we have the exposure of darker ice, lower albedos, which result in more absorptions of solar radiation. And both these processes actually result in a local melt climate, very close to the grounding line. So if you look at satellite images across Antarctica and you look for melt ponds, you always find them very close to the grounding line, and for a lot of ice shelves, you'll find them very close to the grounding line. But we're currently still underestimating these melt-albedo feedbacks. If you look, for example, at the difference in albedo between a regional climate model, in this case the RACMO regional climate model, and the MODIS satellite record, you get the picture like this. So this is done on the climatology, so on a monthly climatology of mean albedo for Dronning Mountainland. And then you actually see that typically there are large differences in how a climate model sees the albedo of the Antarctic ice sheet, specifically for the ice shelves, where actually all these blue areas, so these blue areas on this map are actually areas where the climate model thinks that the surface is way brighter, and so the albedo is much higher. And these are actually also the areas where we see most of the melt. So these low albedo areas are actually being missed by most climate models. And we're actually also missing this albedo feedback in much of the satellite record. If you look at melt estimates, here at melt estimates, for example, from the QuickScat, but you basically see the same processes from passive microwave or other scatterometers. You would see that, for example, over Amery ice shelf, there is a hotspot of melt here close to the calving front, and in this interior, close to the in this area here, basically there is very little surface melt being estimated by these scatterometer or passive microwave melt records. However, if you look at optical satellite imagery, you clearly see these signs of melt. You see that there's these lakes forming in hydrological networks that actually show that there actually is a lot of melt going on now. I see that there's a question from Allegra. So the reason why we have low albedos in these areas, so for example here on Amery ice shelf, it's very clear. It's a combination of two things. One of them is actually that there's a very strong wind blowing away a lot of the snow. So you have strong, and so the exposure of blue ice, which you clearly can see in this area. Most of the time, this is also an area that is sometimes closely located to nunataks. And with these winds, there's also a lot of dust deposition. So for example, in this area here, you clearly see that the color is more grayish, which is the result of impurities that also get there. So this low albedo can be the result of both blue ice and impurities or dust. But we see it mostly always on these areas with very strong winds. So you don't need impurities to lower the albedo. Also the impurities, if we talk about impurities, we talk about local impurities. It's not like soot being deposited from somewhere else in the climate. It's really these local but if we look at the satellite record, we actually see that we're missing a lot of these melt. We can visually observe it here, but it's not being quantified by the typical melt records. And why is that the case? If we look at these three areas, for example, these three polygons, 1, 2, and 3, red, blue, and green, we see that the typical records that are being used to detect melt, which are microwave satellite records, either passive or active microwave. They use the contrast between the winter backscatter or the winter brightness temperatures and the summer brightness temperatures to indicate that there is melt going on. Typically, it's being based on a threshold method. So you say if the satellite signal goes below a certain threshold, I assume that there is melt. Now, whenever we are in these blue ice areas, like in area 1 or area 2, we see that due to the fact that it's blue ice with a lot of specular reflection, we see that the contrast between summer and winter becomes smaller, and therefore we underestimate the melt. Because if you would look in detail, you would actually see that, for example, here in this area 1, we see that the decrease in backscatter already starts much earlier in the season, which would correspond to actually the development of this hydrological network. Already some melt, where the water concentrates in streams and then eventually in lakes. Now, luckily, I say that we are currently underestimating the melt estimates, both in some climate records and in the satellite records. Luckily, there are opportunities. One of them is the availability of much higher satellite, higher spatial resolution satellite imagery, like, for example, the availability of Sentinel-1, which, for example, allows us now to detect all these meltwater features with way more spatial detail, which can be important because many of these melt features are actually very local features with fine scales. Secondly, because there is the opportunity to improve the climate models. For example, we are currently working, we have a paper in the cryosphere discussions of using satellite observations to improve the estimates of surface melt in a climate model by using a deep learning network. So we provide the model with climate model data like temperature, radiation, and we albedo, but we also provide it with the error in albedo. So the fact we acknowledge the fact that the climate models have difficulties in modeling these low albedo areas, and by providing that as an input to our deep learning map record and training it on a set of manipulated weather stations, we can estimate the amount of additional melt. And if we do that, we can actually see that depending on what the error in albedo is, so if we either are overestimating the albedo or underestimating the albedo, we can get very large differences in the amount of estimated melt. So basically, it's a post-processing tool that allows us to correct the inherent underestimates in our model or potential overestimates in some areas by using the satellite record. And so you see, for example, also here in this lower graph, if the albedo in reality would be 0.27 lower than being modeled in the climate model, we would get a very strong increase in these red areas here in the amount of surface melt. So these are ways to overcome these errors. The same here, for example, if you look at the pixel here on Larsen B, and you look at what the albedo and the surface melt is in the RACMO climate model, we see that actually, and so the model is modeling this blue amount of surface melt, but it's overestimating the albedo. If we compare that then with the satellite albedos, so the yellow dashed lines here, we see that the satellite shows way lower albedos. And if we incorporate these in the model, we can get a way better estimate of melt, and we can also get better, and in this case, higher estimates of melt. I see there's a question from Olga. So yeah. Yes, AWSs measure albedo. They actually measure incoming and outgoing shortwave radiation. From that, you can calculate albedo. So in this case, to train the model, we manipulated the weather station. We manipulated the melt record. So we actually took the weather station, but the melt is always being calculated by running a surface energy balance model. So we can tune what the differences in albedo are and use that to estimate the amount of melt. I see there's a second question. Is RACMO driven by reanalysis? Yes, it is. Very short answer. And then the next thing, so we already know for hydrofracturing, we need to know how much water it is. We need to have enough water, but we also need to know where it goes. Because water does not always stay in the firn, and specifically for hydrofracturing, we need ponding, we need accumulation into crevasses,
So we need hydrological transport. And if you look at, if you're on an ice shelf, or in this case on the Novo base, the Russian base, close to Nivelsen ice shelf, you see clearly that the ice on such an ice shelf can move. You clearly see the development of this hydrological network here, and the actually rivers running on these ice shelves. The same here, this is on the Robodoin ice shelf. In the middle of an ice shelf, even there you can have small topography and the transport of meltwater in these small streams that then eventually reaches, in this case, into moulasse, so vertical cracks in the ice shelf where the water drains until the bottom. So here you see the water actually draining from the ice shelf. And if you then try to put the camera close to it, you would see that the meltwater drains into this ice shelf. So there is always there is this transport of water, and understanding it is important because the transport, the hydrological network, can be stabilizing. If the water just runs to a waterfall and runs into the ocean, the potential of hydrofracturing is being removed. On the other hand, if there's a lot of crevasses and lakes forming, the potential of hydrofracturing increases. And there's also the unknown water. We've now looked at the surface water, but there's also, for many of these ice shelves, also water below the surface. So this is me drilling on an ice shelf where you see that if you look into drilling hole, there's the water table is a couple of meters below the surface. If you then lower a GoPro into this hole, you gradually migrate into the ice, and so you see the individual ice bubbles within the ice, and then a couple of meters below the surface, you actually see the presence of these large subsurface lakes. So a lot of the water in Antarctica is actually also just being within the ice shelves. And how does it get there? It's actually a result of having open surface lakes that then refreeze in winter, and so you get these pockets of lake water that are encapsulated within an ice shelf. Here you see in the Landsat time lapses where you basically see the filling of these lakes and then the gradual refreezing again. And these lakes can also collapse. So if you then look at the longer time scale, and you revisit them, you might see these large ice blocks, which is actually the result of these individual lakes that then gradually refreeze in winter and then might drain. So actually drain where the top part of the refrozen lake drops. So you see a strong elevation change, and you see these remnants of lake drainage on these ice shelves. Again, to give you a bit of indication, how does this water go? If you look again at Nivelsen ice shelf, all these blue areas here are blue ice. Here you have some fern, and if you then look into detail, you actually see how these hydrological networks form. If you look in this area here, and you move you actually see how these hydrological networks form, then refreeze again in winter, forming subsurface lakes, and then again result in the new development of a hydrological network. And so now with new data and new remote sensing approaches, we can get estimates of where the water goes. We can run hydrological networks, and we can estimate based on high resolution elevation model data. We can actually build such hydrological network where you actually see that the lake network you just saw by the satellite nicely corresponds to how it would flow on the normal surface. And at the same time with ISAT, we can estimate the lake depths, the water depths, so we can get an idea of where the water actually goes.
we can use SAR or INSAR images to get an idea about the refreezing. So if you have a lake here and you look at the interferogram, so basically at the differences in phase between two individual satellite overpasses. So if you look at these differences in phase, you actually can see a displacement. If you then come back a bit later in time, you actually see these fringes, which is the movement of the ice shelf due to tides, for example. So you actually see a displacement due to the movement of the ice, but you completely lose this displacement over these lake areas because actually there's this water ice interface which is completely non-coherent, so you can't see any signal there. If you then look gradually over time, and you see that these fringes slowly come back, so there's no coherence here. You gradually see the fringes coming back, and so with satellites we can get estimates on how these meltwater features refreeze. At the same time, if we're lucky, we can actually even see these drainage events. So with these fringes, we can estimate vertical displacement. So at the moment that a lake drains, what happens is that the ice shelf bounces back. And these are things we can see with satellite. And so this is kind of an overview of what we can measure from the top. If we look at from a satellite imagery. At the same time, we can get estimates of melting from the bottom. Remember that this melting from the bottom is a key driver, probably the most important driver for the mass loss in Antarctica at the moment. Hydrofracturing is a fascinating and a spectacular event, but the hydrofracturing events are still limited in the current climate, whereas melting from the base is a key component that actually already plays a very important role at the moment. Now we can estimate these basal meltings, basal melting from altimetry, as being done in this paper from Adusumili, where we can estimate basal melt from altimeters like LiDAR or cryosat radar altimeters. But we can also estimate it from high resolution photogrammetry. One of the nice data sets to do that is the REMA data product. So it's a reference elevation product derived from high resolution optical images, and it gives us elevation products over Antarctica at 2 meter or 8 meter spatial resolution. Where for a lot of these areas, we actually have a lot of images. So we can actually use these images to estimate changes in elevation, because these REMA strips are individual satellite observations, for example, like here over the Dodson ice shelf. So we have individual strips for 2015 and we have individual strips for 2011. And at the other hand, we have elevation data, for example, from Operation Icebridge, or in this case, so an airborne campaign, or from cryosat, a LiDAR, a radar altimeter. And we can combine these to get spatial coherent estimates of, with a very high resolution of basal melting, because these altimeter data, they're typically only point measurements, and there's a large set of point measurements, so we get some spatial coverage, but we don't get a complete image coverage as we would have with the REMA strips. So we're currently working on getting these REMA strips corrected, so by applying tide corrections and advecting them, applying some tilt and bias corrections to get some estimates of the basal melt rate. And if we do that, we can get basal melt rates in an Eulerian perspective, so just looking at the same spot over time. But of course, as ice moves, if you look at the same spot in an Eulerian space, actually you're looking at the differences in ice movement, and you're not looking at the differences in melt. And now we can also look at these in an Eulerian and a Lagrangian time frame, so accounting for the fact that the ice moves. And if we do that based on these REMA strips, we can get very detailed estimates of the basal melt patterns. So actually what we see here in these figures are spatial patterns of melt, where you clearly see that, for example, here for the Dodson ice shelf, there's this channel below the ice shelf where all of the melt is being concentrated. And so actually, if we talk about basal melt, it's not a uniform number per ice shelf, but there's actually a large spatial variability where we see that most of the melting is happening on these hotspots, on these basal channels, which can have strong impact on the future stabilities of these ice shelves. Because that brings me to the third component we look at, and that's the role of damage. So, and this is what I'm going to show you now is some results of a paper we published last year in PNAS, looking at damage. And if you look, for example, at Pine Island Glacier, at a long-term Landsat time lapse, you see a couple of things happening. One of them, for example, is that you see that the calving front strongly reduced, where it was in the 90s, the calving front was still here. If you go to the more recent images, we see that the calving front strongly retreated. But what now drives these changes? Pine Island is one of the fastest changing glaciers in Antarctica. Now, what drives these changes? Jan de Rit and his team did a test, a modeling test, basically to see if they could explain the changes over Pine Island Glacier. And in their model, they quantified the role of calving, the role of ice shelf thinning, the role of inland thinning, the role of rheology, how much did the ice change, or the role of sliding, and which of these parameters actually explains that Pine Island has been changing so much. And to do that, they basically run their ice sheet model for 1960 and 96, and for the 2016 scenario, where they changed each of these parameters to see how much of these parameters could explain the observed change. If you then do that, for example, for the calving rate, the ice shelf thinning, the inland thinning, or the combined effect, you actually see that none of these processes actually can explain the changes in flux through the gate. For example, this combined effect for gate number 2, which would be this black line here, only explains 64% of the actually observed changes. So there is something else that is actually explaining these changes for Pine Island Glacier that is not being caught here with by only changing the calving rate, only changing the ice shelf thinning, only changing the inland thinning, or their combination. And what Jan de Rit and his team identified, actually, that to explain these changes over Pine Island Glacier, we need two other components. We need a change in sliding over the inland part of the ice, and we need a very strong change in the rate factor or the rheology of the ice over the Pine Island ice shelf. And if you look at this map, so to get the observed fluxes, we actually need to completely change the rheology of the ice in both of these in these shear zones, these areas here in red. Now, if you look again at the Landsat animation, we actually see that there has been a very strong change over Pine Island Glacier. If you look, so this red area here is actually this shear margin here, and if I play the movie again, you clearly see that where this shear margin was basically intact in the previous decade, it shows a very strong development of damage, crevasses, rifting in the shear margin. It's also very clear in the Sentinel-1 record. If you look at the Sentinel-1 record with the zoom area here, we see that this area actually has been completely, it's tearing itself apart, where it was mostly intact. We see the very strong development of these crevasses, even melange type of open fractures, where basically this complete shear margin has been weakening. If you look at it from an airplane, so this is some NASA Operation Icebridge imagery, you basically see how the shear margin has been weakening, where basically this is how the shear margin looks now. It's no longer an intact ice shelf, but it's this combination of damaged ice that results in a very weak shear margin, and that's actually been a very strong explanation of why we've seen these changes over Pine Island. Because actually, wherever we see these very strong changes, this is also where the shear stresses are the largest, and where the principal component that drives the damage is also the largest. So you clearly see that wherever we see the damage development is also the area where we see a strong indicator of development of damage. And basically, we also see the same even on Thwaites Glacier, where we also here in the shear margin, we see the development of damage. If you again look in an animation, you would see that also here, this shear margin is starting to fracture. And with the fracturing, it's starting to weaken. Now, this damage typically occurs in the areas where the ice shelf is thin. So always on these thin areas, and where there's a very strong gradient in velocity. If you look at the velocity over these two transects over time, we basically see that the gradient in velocity has been steepening a lot. So basically, in these shear margins, we see very strong gradients in velocity. And we now, in our paper, we have hypothesized that actually there is a damage feedback process going on, where we, due to different weakening reasons, can be melting from the bottom, can be loss of pinning points. We see a speed up of the glacier, and we see enhanced shearing. And due to this speed up and enhanced shearing, we get the development of damage. And once we have this damage, basically the ice shelf starts to break, and it speeds up and it shears even more by the fact that we lose some of the resistive stresses. And to test this hypothesis, we used an ice sheet model, so the bicycles ice sheet model with the continuum damage mechanics module developed by Simon Sun, and we tested this hypothesis on an idealized setup on the MISMIP plus setup. So in this setup, you get a glacier that looks like this. You have an ice shelf here on the right, where the grounding line is here. And in this setup, if you run it with your bicycle continuous damage model, you can estimate how damaged an ice shelf or the ice could be, where you clearly see that in these shear margins, there is more damage than on the interior, and the ice shelf is also partly being fractured, because the colors here, the pinkish colors, indicate the integrated damage, so how much of the ice is actually being fractured. And to test our hypothesis, we actually introduced damage close to the grounding line at the locations where we observed it. And if you then compare in the lower part a model run where we introduce damage and a second model run where we don't introduce damage, we clearly see that on this lower part, whenever you introduce damage, these ice shelves starts to fracture way more, and the damage is kind of a self-enhancing process, and even also the retreat of the grounding line. So basically, by weakening the glacier at its weakest point, close to the grounding line, we are introducing more damage, and we kind of introducing this feedback process. Very, very similar to what we observe. So if you would put a satellite image more or less on the same scale, you clearly see that wherever we introduce this damage, we see the development of these damaged shear zones. Now, if you then do this in the same model, so this is going to be an animation. Let me already run it, and then I'll subsequently walk you through each of the different sub panels. So if we then repeat this experiment for 100 years, and we look at what the damage fraction is for two scenarios. On the one hand, we have a local damage scenario where we kind of localized introduced damage. A second scenario, we work with channelized melting. Basically, these channels, which I also indicated, these channels of basal melt that typically also form close to these ice shelves. And if we then calculate what the damage fraction is, the thickness change and the velocity change. So on the right-hand side, you see it for the channelized melting. On the left-hand side, you see it for the local initiated damage. And then you compare how the grounding lines behave. You clearly see that basically both of these weakening scenarios, both the channelized melting as the local initiated damage are very effective scenarios to weaken these glaciers. If you weaken these ice shelves on their weakest spot, you actually have a velocity change, a thickness change, and a change in damage fraction, which correspond to what we observe. Also, if you put it in a spatial model, if you put damage in the bicycle's continuous damage model over Pine Island Glacier, you clearly see that by introducing damage, it kind of expands in a future scenario. So the ice shelves get more fractured and the grounding line retreats, which results in thinning. So by introducing damage, we thin the glacier. We speed up the glacier, and we get grounding line retreat. So if we compare a no damage scenario with a damage scenario for grounding lines for the next 100 years, we clearly see that it's a very effective process of initiating grounding line retreat. And the important thing about this damage process is that actually at the moment, most of the time, it's not being included in any of the ice sheet models. So if people run ice sheet models, they don't specifically account for these damage feedbacks. Sometimes they indirectly do it by changing the rate factor. And our point is actually that these damage feedback can be very, very important because they can have a very strong impact on future sea level rise, and they should be included in our climate, in our ice sheet. And then as last part of today, I want to explain a bit of what we're taking after the paper was being published, how we're now trying to get even more information from the damage signal. So one of our PhD students is actually working on detecting these damages. And I've already shown you a lot of satellite animations where you actually with your own eyes can see the development of these damage areas. But we're now working on quantitative indicators where we can actually also detect it over the complete satellite record. So it's no longer a visual observation, but a quantitative measure. And we can quantify change. How much did it change over the entire Antarctica? And for that, we're currently working with different image transforms. For example, by using the Radon transform, as you would see here on the lower left, we found a very efficient measure to quantify damage. So if this is the original image, and these are some other not very well performing image processing techniques, we see that with the Radon transform, we can very well find these damage areas. And additionally, we can also identify, by using the Radon transform, we can also identify the orientation of the crevasses. And by knowing the orientation of the crevasses, we can actually determine which type of stresses are at play. Because if you compare the stress relative to the velocity field, we can classify the different stresses and how they affect the different damage. And if you then put that into a time series perspective, if you apply these technique on the satellite records, we can start quantifying the change in these damage over our ice shelves over Antarctica. And at the moment, we're working on translating this technique on an Antarctic-wide assessment to get an idea of where they are at very high resolution, where we're making a crevasse map and a damage change map. We're doing that by a combination of using both optical images and SAR images, where the optical images have the advantage of being sometimes less noisy than the speckle sensitive SAR images, but the disadvantage is that we don't have optical images during polar night, so we miss large parts there. And then lastly, another component we're actually working on is trying to understand this damage history in a Lagrangian framework. For this, we're using the velocity fields on a grid base to actually see how each of these points move in time. So you can quantify the movement of each of these individual grid points. And then based on the displacement of these individual grid points, we can calculate the strain or the stresses, but not in an Eulerian framework, but in a Lagrangian framework. So we're looking at how the ice changes, but over time, because we take the history of the ice into account. So you can then, for example, here for Thwaites, again, see the movement of the ice, so the dominant strain direction, taking into account the history of the ice, but also the types of strain. So by and thereby really taking the history. So we're looking at how the ice behaves through time to see if it can be used to explain some of the fractures or some of the changes we see. And if you do that over Thwaites, you get something like this, where some areas clearly have a strike slip pattern, other are more extensive areas, other are more shortening areas. And if you do that over Pine Island Glacier, for example, you see the same, where the main tongue is mostly extension. You have these very strong strike slip areas in these shear zones, which are actually also the areas where we actually at the moment see where the ice shelf is tearing apart. And with that, I would like to conclude. So my basic point I wanted to make today is that ice shelves are the key uncertainty in the Antarctic contribution to sea level rise, specifically on the shorter term. On the longer term, once the ice shelves are gone, of course, there's other major factors at play. And there's these three uncertain processes that still are very poorly quantified and or understood in most of our sheet models or climate models. The hydrology, the basal melting, and the damage, because each of these processes are often fine scale processes that act at very fine scales. I think I've shown you a lot of images where you either see that these lakes or these basal channels or these damage areas are actually fine scale processes that are not easy being captured in coarse resolution modeling. But at the same time, I wanted to show you that there's actually a lot of opportunities and that we're actually living a bit in a golden age, I would say, where both satellite images and modeling are making this step to get these fine scale resolutions and to get these processes there at the right scale to better understand what the future contribution of Antarctica to sea level rise might be. And with that, I would like to conclude. I'm more than willing to take any question.
Thank you very much, Stef. It was fascinating talk. Do we have any questions for anyone? Feel free to raise a hand, mention it in the chat, or just speak out. That would be great. Give people a moment. Maybe I can ask a question. I'm fascinated by this notion of damage. Can you maybe speak a bit more about? Maybe I missed it, but when you refer to damage, you're talking mainly about things such as crevasses and I suppose other features within the ice. are a lot of these features created in a deep historical sense? So maybe from a long time ago, and this is kind of like stored in the ice and is being expressed as it comes into the ice sheet, or are you talking more about events which occurred recently associated with atmospheric variability?
You always, yeah, ice always, there's always crevasses in ice, of course. So it's so if you're in the field, it's always a danger to fall into one. But I'm here talking about like real deep penetrating damage on ice shelves. And I think if you look, for example, on the changes over Pine Island, I think it nicely illustrates what is going on there. Is that the fact that the system is getting perturbed. So the ice is speeding up, or a lot of the glaciers are speeding up, but not all of them are speeding up equally. So I think, see, I think this one. So you basically, if you, by the fact that you get very strong gradients in velocity, the stresses and the strains start to increase a lot. And at the same time, we see melting from below. So the ice shelves are getting thinner and they're speeding up, but not everywhere equally, I think. Did I have it somewhere. No. And that generates these damaged areas. So for example, if you look across these transects and you look at what the velocity distribution of the main trunk was in 1995 versus now, basically it almost doubled in speed. But of course the ice here at the edges did not double. So basically the stress you get into this area increases a lot, and that results in the fact that actually these things start to tear apart. And I think that's the main changes we see, and that also explains why it happens on relatively short time scales. That you actually see, if you look at a couple of years, you actually see it happening. If you again, if you look at this figure here, for example, in 2015 it was still intact. There's a couple of crevasses and a couple of rifts, and there's already this damaged area here. But if you look at this zone here, for example, and if I now start playing it a bit, perhaps I should speed it up a bit, you actually see that how this actually whole piece is tearing itself apart, and that's just because the velocity gradients and the stresses are no longer compensated by the ice, and the thing tears itself apart.
Is this associated with topography? So you have sort of topography that is pinning a section of the ice,
yeah,
creating this shear. So it's specific topography, regional topography differences, which are perhaps creating some of these instabilities.
Which are creating some of these instabilities in combination, of course, with if Antarctica is losing more ice and it's speeding up and it's melting away faster, then these gradients will become bigger. Because of course these locations where the thing is being pinned or where it's being constrained by topography, there the ice will always move slow. So the contrasts become bigger, and that's the reason why you see that happening. And then even now in this case, it's even a bit different, because here you have a pinning point, or here you have some topography. So there it's actually a local feature that actually tears away. But here it's really the differences in speed across the ice shelf that results in this weakening in combination with the thinning, because this is also an area where the ice shelf is thin, and where we do see some of this basal melting. So where the ice shelf is getting thinner and thinner and thinner. So it, in that sense, it's a feedback process that comes late in the chain. It's if the ice shelf is getting weak, it kicks in and it speeds it up even more. But it's not because it's kind of a final phase of an already weak ice shelf. The difficulty is that once it kicks in, it's very difficult to stop. And so you see, for example, that, and it's also kind of, if you would ask me how Pine Island would continue, I think that over the next decade, we'll completely see this whole area showing a very similar pattern. I see there's a question of Lawrence.
Yeah, great talk, Stef. I had a question about whether there were any healing processes that you could imagine going forward over the next decades and century.
I think it's not very I think it's not very easy to as a healing process. I think if you, for example, for this case, if you would like to heal it, then basically all the ice should go faster, so you get more compression again, and the ice shelf would heal. I think that's also a bit the difficulty, is that once it kicks in, it's rather difficult to stop. Now the potential advantage is that it's a very local process, so if the buttressing locally if it takes over by something else, then of course the ice could slow down again. It's really this. But one of the hypotheses we had is that it's an important process because it's very difficult to stop.
Yeah, I wasn't really referring just to the shear margin issue, but more generally, are there precipitation changes, extra snowfall, or
You mean,
anything else that could act as a negative feedback on?
Yeah, I think that definitely is. I think also the way we model the damage is in a still way a very simplified thing, and we also know that, for example, within rifts, ice melange or these type of things can have a very stabilizing effect. So in that sense, I think to really quantify what the effect would be, you really need to dive even deeper into this process, because indeed even refrozen sea ice or types of melange could also provide some of potential healing, I think. I don't know if that was what you're referring to.
Well, I don't have a good answer. I was just trying to see what you thought.
Yeah, but so my idea would be, one of the processes could be that if it freezes over again in these damaged areas, that could have a stabilizing effect. If that would be enough to actually stop it and to go back to a completely healed ice shelf, that I doubt.
Because there's a temperature sensitivity to the ice rheology, right? So possibly warmer, frozen, new precipitation might be better than brittle fracture, brittle cold ice fracture.
Yeah, that's another potential indeed, that the temperature of the ice would change the fracture dynamics, and I think that's actually also the reason why in the paper we identified the process, but we didn't want to actually run a projection for Pine Island, because there's so many uncertainties of what temperature you put in there. Like if you put it into numbers, it can become complicated, because you don't know how to put them. But I think the main point we basically wanted to make is that it might be an important process, and it's important for us to get to start to nail it now and to better understand it, to better quantify it.
Okay, thanks.
Thanks, Laurie. Do we have any other questions? We're a little bit over time here. I see quite a few people are filtering out.
If not, then thank you very much.
Allegra says thank you. Thanks for joining us, Allegra. Okie doke. We should probably close out here. It looks like everyone's fleeing. We're about 10 minutes over, but thanks so much for your talk. It's fascinating. I look forward very much to adding it to the YouTube collection.
Yeah, you're welcome.
Yeah, it's fascinating.
Thanks for having me. And
seeing as, can I ask you another question?
Of course.
Yeah, so when I was talking before about your notion of damage, I was intrigued to wonder if there was some sort of like deep history, perhaps, within the ice that the ice might remember, 100,000-year time scale previous events, and therefore create structural vulnerabilities that would add like another layer of instability or
Ooh,
I mean?
that's a difficult one. To be honest, I wouldn't know. I think on a very long time scale, it might be difficult, I guess, but I'm not enough an ice rheologist to have an answer. The thing we're trying to do now with this Lagrangian framework is already take the short history into account. Because the problem with stresses and strain is that people most of the time only calculate them on an instantaneous thing. So whereas ice, of course, there is some history going on. But of course, we are limited to the satellite velocity products, and so we can basically go back a couple of years, but not what you would call deep history. And I have no idea. It's a very good question, but I don't know the answer of how ice rheology would react on a very long time scale.
Can I ask you another question about the recent history then, particularly for Pile Island Glacier? I think people really emphasize the importance of ocean warming, right? Increases in heat content. But perhaps I wonder if your work maybe suggests there's also an important role being played by atmospheric warming and perhaps damage from melt ponds, damage the surface. Is there some sense perhaps?
I think our hypothesis was that damage is playing a very important role. I think it's also, if you look at the RIT paper, you can see that actually melting from the ocean cannot explain it alone. And so there is something else going on. In terms of atmospheric processes, Pine Island is still a very cold region. And also the amount of surface melt is very limited. So I don't think that surface melt plays a key role here in the current climate. By 2100, it might be different. But in the current climate, I don't think that the role of hydrofracturing plays a role here. I think it's basal weakening in combination with the damage feedbacks that explains what is going on for this region. And I think for most of the Antarctic ice shelves in the current climate, that is the weak spot. By 2100, if there's way more surface melt, hydrofracturing can also play a very important role, of course. Yeah, that would be. I don't know if it answers your question.
Yes, yeah, I think it does. But thank you again for your time, and yeah, I look forward to uploading. I hope you have a good rest of the day.
Yeah, you too, and thanks for having me. Bye.
Take care.